So a lot of these rules we've actually worked with before. We've never talked about them formally, though. So the product rule, that's the one that we've actually seen the most, which says when you're multiplying like bases, so let's say I have x squared times x to the fifth. What do you do with those exponents? Add them. We've done that a lot. We've just never had a name for it. It's called the product rule. So when you multiply like bases, you add the exponents. We just took 2 plus 5. We get x to the 7th. So we've worked with the product rule before. We've also worked with the quotient rule. So this is when you're dividing like bases. So let's say I have y to the 6th and I divide it by y squared. What do I do with those exponents? Subtract. So you take your y and you just 6 minus 2, it's going to be y to the 4th. So we worked with that one mostly when we were factoring. A little bit multiplying, dividing our rationals as well. Now the power rule is not one that we've done before in this class. Again, this is actually a table I use when I teach 082. We fill it out in 082. This says if I'm taking, let's say, x to the 3rd and I'm raising it to the 4th power. So x to the 3rd raising to the 4th power. So if we think about it, that means I have x to the 3rd times x to the 3rd times x to the 3rd. That's what the 4th power means, right? We're multiplying x to the 3rd by itself 4 times. So if I have my multiplication by product rule here, product rule says we do what with the exponents? Add them. So 3 plus 3 is 6, plus 3 is 9, plus 3 is 12. But that would be really labor intensive if I gave you big exponents. So if we know the answer is x to the 12th, and we're looking at power raising it to another power, what do you think the shortcut is to get this answer x to the 12th? What are we going to do with the exponents? Just multiply them. So if you have power to a power, you're going to take these numbers and you're going to multiply. So you get x to the 12th. Again, this is y, but if I give you something to the 50th power, you're not going to sit there and write it out 50 times so you can add it up over and over. Just multiply. Just multiply. So any questions on those first three? Now the next two are very, very similar. It's product to a power and quotient to a power. And I always say, think of these like distributing. So if I have, let's say, 2x squared y, and I want to raise it all to the 3rd power. Well, I could write it multiplied by itself 3 times, but again, that's not necessarily practical. Think about it like distributing. So I'm going to take that 3rd power, and I'm going to put that 3rd power on every one of my bases, even the number. So everything gets its own 3rd power. And now we need to simplify that. So starting with our number gets the exponent as well. Whenever you have a number raised to a power, positive or negative, you have to evaluate it. It's not simplified if you leave 2 to the 3rd. So what's 2 to the 3rd power? 8. 2 times 2 times 2. Again, you can get that from a calculator. If you're looking at that in your calculator, you take 2, find this key right here, raise it to the 3rd. That's how it looks on most calculators. So 8, and now we're starting to cross rules. So this is where you've got to be really careful with your rules. If I have x squared and I raise it to the 3rd power, what am I going to do with these 2 exponents right here? Multiplying. So now we're putting the previous rule in. So we have x to the 6th, and then this is just y. It doesn't have an exponent, so we can go y to the 3rd. So you may have to, these problems do sometimes involve more than one operation, more than one of these exponent rules. And then quotient to a power is the same rule, except it starts out as a fraction. So like if I have 4 over x and I want to raise it to the third power, you just distribute that third power to every base inside. So just like when we had it in as a product, we're just going to distribute to every base inside. So I'm going to have 4 to the third power over x to the third power. And if you had more variables, they would all get the third power. Rob?
So I guess the difference between the two is one's division, one's multiplication?
That's it. Yep. Product, so this one's multiplication. Quotient means division. It looks like a fraction. Yeah, that's the only difference between these two, is this one is division, this one's all multiplication. Do you think this answer is simplified? No, all those numbers raised to the power, throw them in your calculator. 4 to the third is 4 times 4 times 4, 64 over x to the third. Negative exponents, we've run into them back in the beginning of 10.2. And we saw something like just a number raised to a negative exponent. And what did we do when we had a number and it was raised to a negative exponent? How do we make that exponent positive? Put a 1 on top. So this goes back, if you just flip back a page in your notes actually, we had negative exponents on some of these problems. And to make those negative exponents positive, all we did was go 1 over our base now with a positive exponent. Do you think that answer is simplified? No, what can I do to simplify that just a little bit more? Make that 3 squared into a 9. Now, we don't always have to just throw everything under a 1. So let's say, we'll do 2 examples here. I had 2x to the negative 4th y to the 3rd. And we want to write it with positive exponents. So my question is, which of those bases, there's 3 bases there, 2x and y, those are our bases, and then the little number is the exponent. Which of those bases have a negative exponent with them? X. X is the only one with a negative exponent. The other 2 have positive exponents. We don't see one on the 2, but there's really a 1 there. The y has a positive 3. So the only part that has to move down is the x to the negative 4th. Everything else can stay behind because it has a positive exponent. So the reason we use the 1 in this problem is because our only base had to move. But here, only one of our bases has to move, and that's the x's. So the x's are going to go down, but the 2 and the y to the 3rd don't need to move. Their exponents are positive. So we don't always have to send everything to a denominator and put a 1 on top. It's only if you have a negative exponent on that base. If you only have one base and it has a negative exponent, that's when it's the 1 over. There's nothing left behind. And then our last rule, 0 power. I don't know if we actually see this in this class, but it's always good to know. What's anything to the 0 power? 1. Anything to the 0 power is the number 1. It can be a number. If I had 427 and I raise it to the 0 power, always the number 1. So people usually don't like that, just accepting that that's the number 1. So let's put 2 of our rules together and see why. This is why. If I take any quantity other than 0 and divide it by itself, what do I get? So like, what's 2 over 2? 1. 5 over 5. 1. So what do you think x to the 3rd over x to the 3rd is? 1. 1. Think about factoring. If we ever factored a term out completely, what did we always leave in its place? 1 because we divided it by itself. So we did this sum when we factored. If you factored something out, divided it out completely, there was always that 1 behind. So when you divide anything by itself, it's the number 1. But let's go back to our rule up here, our quotient rule. When we divide like bases, what do we do with their exponents? Subtract them. So if I was to be using my rules of exponents, I'd say this is x to the 3 minus 3, which gives me x to the 0. And what did we just say this was also equal to? 1. So anything to the 0 power is 1. That's kind of your little reason why. So if you divide these out and they're the same, you get 1. If we use our rule of exponents, we subtract, we get x to the 0. So x to the 0 equals 1. Anything to the 0 power is 1. If you don't remember it, put it in your calculator. It remembers. It will tell you it's 1 and not 0. So what we're going to do, our directions here, are to use the properties of exponents to simplify each expression, write with positive exponents. So you've got to make sure all of your answers have positive exponents, no negative exponents. So if you took 082, there was the same stipulation, no negative exponents. So what we're going to do, how we make this an 083 topic versus an 082 topic. A is an 082 question. B is an 083 question. The only difference, we make the exponents fractions. The rules haven't changed. People get freaked out because they see there's fractions. They're like, fractions, oh no. Rule's the same. So we're going to start with a rule with our integers, so we remember our rule, and then we're going to apply the same rule to fractions. So x to the 5th times x to the 4th, product rule. When I multiply like bases, what do I do with their exponents? Add them. This is the one we worked with the most. So if I have x to the 5th times x to the 4th, and we don't have to write this step, I'm doing it just so we recognize what we're doing. We add the exponents, and we get x to the 9th. So this right here is the product rule. And what we did was we added exponents. So one of your extra credit questions that you're actually going to have to go back and do, the 10.2 exponent questions. When I say, let me see what my question is. Summarize the rules for exponents. Product rule. When you multiply like bases, add their exponents. That's your summary of the product rule right there. So when I look at B and I'm multiplying like bases, what do I do with their exponents? It's the product rule. When I multiply bases, what do I do with the exponents? Add them. It's the same rule. It just looks worse because there's fractions. But I'm going to take my exponents 2/3, 5/3, and add them. Can I add those fractions right now? Yes. Why? Common denominator. So now we're going back to 081. Can we add or subtract these fractions? Yeah, they both have a denominator of 3. What part of the fractions do we actually add? The 2 and 5, the numerators. So we have 7/3. Now don't confuse this with the start of 10.2. In the start of 10.2, we wrote in radical notation. It was part of our directions. There's nothing in your directions that say use radical notation. It says use the properties of exponents. That was our properties of exponents. You don't need to switch the notation to radical notation. It's a separate topic. And that sometimes confuses people, but directions, a wondrous thing, use the properties of exponents to simplify. That's our exponent rules. Questions so far? And I'm not going to give you long, complicated problems like you see in 082. It'll be really just a test of do you understand what the different rules are. So for C, I have 4 to the 6th divided by 4 to the 4th. These have like bases. Their bases are 4. Even though it's a number, it's still a base. They still have them in common. And while you could expand both of those numbers and then simplify the fraction, you'd be wasting a lot of time. When I divide like bases, what did I do with their exponents? Subtract. So I kept my base and I just subtracted the exponents. We've done this before on a variable, but it works for numbers. So if I subtract my exponents, I get 4 squared. Do you think that answer's simplified yet? No. Numbers you have to evaluate. No matter what kind of exponent they have, numbers you need to evaluate. So 4 squared is 16. And we can work out this problem without a calculator. Otherwise, if you're trying to evaluate first, you're going to need a calculator or a lot of time. So if we do the example right under that, this is our 083 example because we have rational exponents, they're fractions. When we divide like bases, what are we doing with those exponents? Subtracting. So we keep our base, we keep the 9, just like we'd keep an x or we'd keep a y, and you take the first exponent and subtract the second exponent. So whenever you divide like bases, you subtract the exponents. That's your quotient rule. That's a sentence on your extra credit that would satisfy that question. When you divide like bases, you subtract their exponents. Am I ready to subtract these? Yeah, they have a common denominator, so I subtract the numerators. So I'm looking at negative 10 fifths. What do you think I might do next? Yeah, simplify that fraction. Negative 10 fifths. I can simplify this fraction a little bit more. It actually divides out evenly. So I get 9 to the negative second power. So I'm looking at 9 to the negative second power. Go back to our instructions from before. Never evaluate a number with a negative exponent. Never evaluate a number with a negative exponent. How do we make negative exponents positive? We're going to do that 1 over. So we're going back. Before we always had a rational exponent that was negative, but now it's not, and that's fine. It's actually a little bit easier to work with. Negative exponents on numbers, you've got to make them positive first. If you type this into your calculator, you'll see right away it's not negative 81. It's going to give you a small decimal. So if you're ever in doubt, try it in your calculator and see what your calculator thinks. To make my negative exponent positive, we go 1 over, oops, I skipped a step, 1 over 9 squared, which is 1 over 81. Yeah. Yeah. You would just simplify. Yeah, so like if you had, let's say 9 to the 4 6, you would go 9 to the 2/3 and then go from there.
What if it wasn't even though? What if it was like 2 over 7, 9 2 over 7?
Then you would actually go, and you wouldn't have an example like this. You would go to that to simplify it. Or you can put it in your calculator because these directions don't require that you use radical notation. But if you're trying to simplify it by hand, you'd go to radical notation. Yeah. Good question. Any other questions? All right, so D, I have x to the 1/4 divided by x to the 2/3. Quotient rule, when you divide like bases, what do you do with those exponents? Subtract them. It's the same rule. The rules don't change. So this is our quotient rule, so we're going to take our exponents and subtract them. And you're more than welcome to do that in your calculator. I'm not testing if you can subtract fractions by hand. That's what I test in 081. So if you want to put that in a calculator, you're more than welcome to. We're going to do it by hand. Take 1/4 and I'm going to subtract 2/3. It's my first step for subtracting those fractions. Common denominator. What's my common denominator for 3 and 4? 12. We actually did problems like this back when we were dealing with the monster rationals. So what am I going to multiply this first fraction by so I get my denominator of 12? Form of 1 made up of 3. 3 over 3. So we get 3/12. And what am I going to multiply this bottom fraction by so I get my denominator of 12? 4 over 4. So I get minus 8/12. Just getting a common denominator. Again, your calculator, if you have a scientific calculator, will handle all of this for you. So I get negative 5/12. Now my answer is not negative 5/12. Where was this negative 5/12 going in my problem? I just moved it over for convenience sake. It's my exponent on the x. So all that work was just to work on simplifying this right here. So I end up with x to the negative 5/12. What's the second part of our directions say for our problems? What do our directions say? Right, with positive exponents. So none of our answers, none of our final answers, according to our directions, should have a negative exponent with them. So how am I going to make x to the negative 5/4 have a positive exponent? Just one base under 1. So it's like this example right here. Whenever you end up with a negative exponent, if that's all that's in your problem, just 1 over x to the 5/12. Move the whole thing, just change the sign on the exponent. Questions? So the rules by themselves aren't bad. There are a lot of them. I will say that this is a very, very small piece of this entire unit. So it kind of stands alone. I'll just leave it at that. It's a small topic. You're not going to get like 8 of these on a test. Anything like that. So E. I have a product and it's raised to a power. Do you remember what the word was I said to think about when you see a lot of things raised to 1 power? Distribute. We are going to end up multiplying. But we're going to just think about it like distributing that 5th power. So we're going 3 to the 5th, and we're going x to the 4th to the 5th. Three to the 5th. Grab your calculator, throw in 3 to the 5th power, or multiply 3 times 3 times 3 times 3 times 3. Does anyone have that number?
243.
243, thank you. And we've got another rule here. X to the 4th to the 5th. When I raise a power to a power, you got it, Sarah, what do? Multiply them. So the time that you add them, and these two do get mixed up frequently, you add them if you have multiplication between the original problem. If you have a power to a power, this is where we multiply them. So we're looking at x to the 20th. So power to a power, power rule, multiply. 243 x to the 20th. So in F, again, I see a product raised to a power. We're going to think about it like distributing that 1/3 power. So I'm looking at 8 to the 1/3 power, and then u to the 5th to the 1/3 power. Now numbers, we have to evaluate all of our numbers, whether or not their exponents are rational or integers. Because this particular section does not ask you to use any sort of radical notation, you could put that in your calculator and just get back the answer. Does anyone remember off the top of their heads, a 1/3 power is always associated with what radical? Cube root. So a 1/3 power always means the cube root. So seeing 8 to the 1/3 power is the same as asking what's the cube root of 8. And that goes back to the start of 10.2. So you could look at it that way again. For this particular question, you could just put it in your calculator. But if we think back to what we did before, the 1/3 power is the cube root of 8. And we don't have to do that with our variables, but since we're evaluating our numbers, we might use that radical notation. So we get 2. And then when I have u to the 5th and I raise it to the 1/3 power, power to a power, what am I going to do with these exponents? Multiply them. So I'm multiplying 5, I'm just going to write this to the side, times 1/3, and that's going to be the exponent on my u. So if you want to see it as a fraction, we can put 5 over 1. There's nothing that simplifies before we start, so you can just multiply straight across. So we get u to the 5/3. And again, we don't have to write variables in radical notation. We only did that for the 8 because we were simplifying our number. Questions? Go ahead and try those last two. I'll give you a couple minutes. Try the last two. So what was the rule we used for G? There we go. What am I going to do with these exponents in G? These two right here. Multiply them. So I'm going to take the -3/4 and multiply it by 4. I can put that over 1 if I want. Now, some of you I saw multiplied straight across and simplified. Works perfectly okay. You get -12/4, and then you made it -3. You could also do one of these before you start. 4 into 4 once. But if you multiplied straight across, you still ended up with -3. I saw that on people's papers. But then I saw a bunch of you stop right there, but our directions said write with positive exponents. So you got to go that one more step, which is 1 over y to the 3rd. And then for h, what do I need to make sure I do with that 6th power? Distribute it to both of those bases. So I've got 2 to the 6, x to the 2/3 to the 6. And then 2 to the 6, just put that into your calculator. 64. And then what do I do with these exponents right here? Multiply them. So we could put that 6 over 1. Again, if you go straight across here, you're going to get 12/3, which I think you'd reduce to 4. You could also do that right here, 3 into 3 once, into 6 twice. It doesn't matter. You get the same, as long as you reduce, you get the same answer. So you get 64x to the 4th. Questions? All right, I actually don't want to start the notes for 10.5, so that's the end of 10.2. I want to just give you a couple of examples to think on, and then when we come back and do 10.5 on Wednesday after your quiz, the problems will make much more sense. So these are not in your notes. Problems are not in your notes. But I want to multiply and simplify. And we're going to call this pre-10.5. Square root of 2 times the square root of 3. This is a problem we've done before. Multiply and simplify the square root of 2 times the square root of 3. Square root of 6. That's our product rule for radicals. So just multiply those radicands together. Leave them under a square root. Square root of 6. Can I simplify the square root of 6? So this will be a good little review too to get ready for your test. The simplify, or not your test, your quiz. Simplify. Can I simplify the square root of 6? It's 3 or 4. Yeah. Again, it's a half sheet. It looks like a drill. Yeah, quizzes are drills with new numbers. That's all quizzes are, drills with new numbers. What's 4 times 2? It's always multiplication. I said, people like to simplify now, and you're going to try to break these up any way you can. Do any of my perfect squares evenly divide into 6? Well, 1 doesn't count because 1, if I take a 1 out, it's just doesn't. That's done. Don't try to simplify everything. How about this one? 2 square root of 3 times the square root of 5. What do you think I can multiply together in this problem? Square root of 3 and square root of 5. These two can be multiplied. They're both radicals. In that sense, they're like. So the square root of 3 times the square root of 5 gives me what? So 15? Square root of 15. You always got to keep it under that radical. Well, I don't know when you say 15. Some people do just write 15. You got to keep it under the box. Keep it under the radical. And 2 up front. How about, let's get some good brain cells flowing today. Let's do 3 square root of 10 times 5 square root of 8. What do you think I can multiply together? What do you say, Shakira? Outside numbers, absolutely. If they don't have a radical, everything here is multiplied. So this problem to us looks like this times this. In reality, this is 3 times the square root of 10 times 5 times the square root of 8. Nothing is tied together there. So we have what's called the commutative property of multiplication, which says, play with that order all you want, it's still the same. 2 times 3 is the same as 3 times 2. And you don't have to write this on every problem. I'm just showing you why. So yeah, we absolutely can multiply, as Shakira said, that 3 times 5, the outside numbers. You get 15. What else do you think I can multiply together? The square root of 10 and the square root of 8. And what do I get them when I multiply those together? Square root of 80. And you could do that right from this form here. My point is just, if the numbers are outside, multiply them. If the numbers are under square roots, or cube roots, or fourth roots, multiply them. Is this simplified? So the simplified part's a big part of your quiz, which again, it looks like a drill. It's only a handful of problems. Can I simplify the square root of 80? Do any of my perfect squares evenly divide into 80? If more than one of them does, I want to know the largest. 16. So you go to your list. 80 would be between 64 and 81. Got a calculator. Even if it's a 5 function, you can still do division on it. Try your 80 divided by 64, 49, 25. Try 36, 25, and then you'll find it at 16. So I'm going to have 15 times the square root of 16 times 5. And then what can I simplify from that square root? 16. And what's it come out front as? 4. And what happens to the 15 and then the 4 that comes out front? Multiply them. Everything here is multiplied. So we end up with 60 times the square root of 5. So how about 7 square root of 6 times 8 square root of 5. What do you think I can multiply together there? And if you understand this, the start of 10.5 is nothing. It's just distributing where you just say, what can I multiply together here? So what do you think I can multiply together here? 7 and 8. Numbers out front. Multiply them together. 56. And then how about the square root of 6 times the square root of 5? Always under a square root when you're multiplying square roots. And then 30. Do any of my perfect squares evenly divide into 30? No. So, we're done. And that's where we'll end today.